Hi everyone, I'm Salvatore Bottaro, and in this talk I'll tell you about how you can probe dark field forces through cosmology. Now, it's a sad fact of life that we are basically ignorant about dark matter interactions, not only with the standard model, but also with itself. So it is crucial to exploit all possible observational experiments to shed light on dark matter dynamics. Now, the dynamics that I'm interested in for this talk is shown in this simple cartoon. So we consider a completely secluded dark sector. So dark matter interacts with baryons only through gravity, but we assume that dark matter particles interact with themselves not only through gravity, but also through a new long-range attractive force mediated by a very light scalar S. So basically, we introduce a new Yukawa-like potential for dark matter here, where beta, this parameter beta parameterizes the relative strength of this fifth force compared to gravity. For the rest of the talk, I'll assume that the scalar is, for all practical purposes, massless. Now, we are in a very good position to explore this scenario, especially thanks to next generation galactic surveys like DESI or Euclid that just went up into space, which will, because they will improve significantly the sensitivity to this kind of scenarios, as we'll show later in the talk. Now, you can assume that this interaction here is generated by this simple term in the Lagrangian, where chi here is the dark matter. Now, there are two main consequences of this interaction. The first one is that S basically couples to the dark matter number density. So once you write the Klein-Gordon equation for S, you find a non-trivial time evolution of the vacuum expectation value of the mediator. This in turn implies, again, through this term, that the dark matter has a time-dependent mass, which, again, implies that in this scenario, dark matter redshifts differently as compared to lambda CDM. And this leads us to the first class of consequences of this fifth force scenario. That is the effects on the background. In fact, dark matter redshifts differently, and this is imprinted in a correction factor to the Hubble parameter here. So basically, this fifth force affects also the way in which we measure distances in the universe. Let me stress that this correction to Hubble has been overlooked in other similar works in the literature. Now, there is a second class of consequences of the fifth force that acts at the level of cosmological perturbations. In fact, the total matter fluctuations driven by this additional attractive force acting on the dark matter component will grow faster than in lambda CDM, and in particular we find that the linear growth factor, the matter fluctuations, receives this correction factor here. Where F dark matter is the fraction of is the dark matter fraction, so 0.85 more or less. We are assuming that for the moment that all the dark matter feels this additional force. And let me stress two additional features of this correction factor. The first one is the log that appears here, which today can be pretty large. It can be of order 10. So at the level of matter fluctuations, the scaling is not simply beta, but beta log. And second, the second important aspect is that at this point, we are only modifying the time evolution. So we are only changing the linear growth factor. We are not adding new spatial features. And the reason is that we are considering the scalar to be massless. So we are not introducing new scales in the game. So the same correction factor acts at all scales. And another consequence is the fact that now baryons and matter fluctuations evolve differently. And this can be seen as a violation of the equivalence principle, as we will see later also. and determines a faster growth of relative fluctuations that now are no longer constant, as in lambda CDM, but they grow with time. In particular, they are proportional to the matter fluctuations. So, and this proportionality factor is simply given by beta. In this case, oops, what happened? Oh, okay, whatever. No log factor here. Okay, so these are the main consequences of this fifth force scenario. Let's see what happens at the level of observables. Let's start from the CMB. So the physics of the CMB can be understood in this way. Now, since we are modifying the interactions of dark matter alone, we expect that all the effects that I mentioned before will be relevant only starting from matter radiation equality. However, the physics of the CMB is determined mostly at the time of last scattering surface, so shortly after equality. So basically, the effects of the enhanced growth of perturbations didn't have time to become relevant at the time of recombination. So in this case, for the CMB power spectrum, the scaling is actually the naive one, the naive beta scaling, because the log here is basically 1. And again, since, as we will see, this beta is pretty small. Basically, we don't change at all the shape of the spectrum of the CMB. What we change instead is, in a sense, the position of the spectrum. This is because the photons of the CMB have to travel all the way from the last scattering surface towards us. So they are sensitive to the different expansion of the universe throughout all the cosmological history. And this is imprinted in the computation of the angular diameter distance. Now, since in our case Hubble is smaller, this delta H is negative, the physical distances are slightly smaller, and so the peaks and dips, so the spectrum of the CMB shifts towards larger L. And this is in fact shown in this bottom panel here, where we show the ratio between the spectrum of the CMB in this fifth force scenario compared to lambda CDM. Now, so the point is that with an early time observables like the CMB, we do expect that the effect of the fifth force come through this projection effect, while instead, where the enhanced growth of the cosmological perturbations becomes really important is instead in late time observables like large-scale structure. And in fact, if you do a simple computation and compute the linear matter-matter power spectrum, you already find the effect of this enhanced growth. In particular, in this plot here, we show in blue the fraction, the ratio between the power spectrum in this fifth force scenario and lambda CDM. So you can first appreciate the fact that this ratio is basically constant, doesn't depend on k. This is because, again, we have no additional scales in the game. So at the linear level, everything, all the corrections that we see before acts in the same way at all scales, and it is compatible with the beta log scaling. At the same time, as I said, we have also larger relative fluctuations. And indeed, here in this plot, we can see the comparison between the matter relative correlation function in lambda CDM compared to the one in the fifth force scenario. So already for beta of order %, we gain at least an order of magnitude, and you can also see how the matter relative correlation function in the fifth force has the same shape of the matter one. This is because, again, the relative fluctuations are proportional to the matter fluctuations. Now, of course, experimentally, you don't have direct access to this kind of correlation function, but you only measure the fluctuations in the number of galaxies. which are related to the fundamental fluctuations, delta matter, delta relative, so on and so forth, through the bias parameters. So when you compute in fact, when you compute the correlation function between delta G, so the fluctuation number of galaxies, all the correlation functions that we saw before enter at the same time and determine the structure of the LSS observables. So the galaxy power spectrum and the bispectrum that we computed in this project. Now, we can recognize two pieces in both observables. The first one is similar to, as the same structure of the lambda CDM corresponding function, so both for power spectrum and bispectrum, and this comes directly from the matter correlation function, all matter correlation function. So the k dependence is the same as lambda CDM. The only difference is in the larger beta log enhanced growth factor. However, in addition to that, we also have new pieces that come from the different relative fluctuations that we have in this case. And these are the interesting pieces in a sense because they contain all the effects of the equivalence principle violation, especially in the case of the bispectrum, as we will see later. However, when it comes to bounds that I'll show now, the dominant effect from LSS comes from this piece here in the power spectrum. So let's discuss for a moment the results of our analysis. So in the gray blob here, so this is beta. The gray blob here show the bound coming from Planck alone. So you can see that already the CMB puts a bound on a beta, constraint beta to be at most the percent level. However, when you add the BAO, which are not directly affected by the fifth force for a similar reason to the CMB, because again, sound horizon at baryon photon decoupling baryon photon decoupling occurs pretty early, pretty close to equality. However, BAO break the genesis, so this improve the bound. So we get a bound of order 5 to 7 times 10 to the minus 3. However, when we can gain a further factor of 2 or 3 once we add the prospect, for example, from Euclid. So basically, including with Euclid data, we in principle will be able to constrain this fifth force at the level of per mil in beta. So as I said, there are a few comments that I wanted to say about this result. So the first is that the LSS contribution is mostly driven by the power spectrum. And the reason is that the bispectrum becomes pretty soon dominated by systematics. What I mean is that we computed the bispectrum only at 3 level. And the one loop correction becomes larger than the signal, the correction coming from the fifth force. Well before so when the constraining power of the bispectrum is still smaller than the power spectrum. So in the end, when you do this simple estimate, you find that the contribution of the bispectrum is pretty small. Besides, because of the log enhancement here in the lambda CDM like part of the power spectrum, most the signal is dominated by the enhanced matter fluctuation. So the role of this this correction factor here due to the relative fluctuation is pretty small. However, this is not general at all. In fact, you can consider a different scenario in which you play with where is the point? Okay, where you play with the dark matter fraction. In fact, if you notice, the beta log term here is proportional to the fraction squared, while the relative term instead it's only linear in F dark matter. So if you reduce the fraction, what happens is that the effect of the lambda the relative weight of the two pieces is switched. So the bound will be, albeit weaker, will be driven by the new special features encoded in the delta B or delta P correction. And yes, 3 minutes. Okay. So in fact, this will highlight several important features of coming from the relative fluctuations and the violation of the equivalence principle. As I said, one interesting one comes from the bispectrum. In fact, if you compute the bispectrum for two different tracers, and consider the so-called squeeze limit, in which you send the momentum of one of the two equal tracers to 0, the bispectrum develops a pole, so the signal will be enhanced, and this is in one-to-one correspondence with the already mentioned violation of the equivalence principle. You can see this in this way. If you consider the two tracers here falling in the gravitational potential generated by the long wavelength fluctuation, this one here, when you move to the free fall system, in which you are supposed to switch off this gravitational potential, instead, either one of the two tracers will still feel residual acceleration. And this is, as I said, directly related to this singularity in the bispectrum. So this plot here shows what the signal looks like when you go to the squeeze limit of the bispectrum under the condition that I said before. So this is the bispectrum minus the lambda CDM value divided by beta times beta lambda CDM. So when K here is still small, so when we are far from the squeeze limit, the signal is dominated by the lambda CDM-like part of the bispectrum, and so you get a plateau because the two are basically proportional, and you get and you start to see a structure only in the squeeze limit. So, for example, if you a few comments here. So first, if you consider the case in which you reduce the fraction of dark matter that feels the fifth force, of course you get a smaller signal. However, the plateau here will become will go down faster than the enhancement of the pole. So the pole will become more prominent. Nonetheless, even in this case, when the signal is dominated by this plateau, basically, it is interesting to think of observables that are sensitive to this new structure. For example, you can consider what we call a pole observable. So this combination of bispectra normalized to the power spectrum that basically removes the effect of the plateau and highlights highlights the peak coming from the pole. Okay, so these are the conclusions. I don't know if how much time I have, but I think I'm done. So, okay, these are the conclusions, and